Welcome back again for the last time. This is really true. Okay, let's conclude this presentation about shot pinning with a subject that is strongly related to shot pinning, but not only to shot pinning. That is much more what we are talking about now is widely applied not only for assessing shot pinning, but in many other fields. I'm talking about residual stresses. We already talked about residual stresses many times. We know the importance that they have in determining the mechanical properties, especially for fatigue of structural components. And then what is important, during my talk, some of you already asked, how can we measure the residual stress? And we said, well, we can use different methods. One is the XR diffraction method, and then there are also other methods. And what I'm going to discuss with you now is this method. And I will focus, after having introduced the concept itself of residual stresses and the different level of scale we can define for residual stress and residual stress measurement, we will focus on what? On the methods that are most commonly used in the industrial practice and also in academic measurement, experiment, let's say, and a special emphasis will be given to XRD, the XR diffraction method, because this is the method that from a, let's say, conceptual point of view, deserve a bit more attention to understand how we can pass from the experimental signal, the diffraction peak, to the value of the residual stresses. And then we will also introduce the other method that can we use, the hole drilling method especially, and the Barkhausen method, that is a method based on the measurement of the magnetic noise, and then can be used also for the measurement of residual stresses. Okay, we have already said that indeed, which is the nature of residual stresses. Indeed, the residual stresses can be induced in many different ways. If they can be induced by some not uniform cooling law that during a heat treatment. What is inducing residual stress is mainly the not uniform variation of temperature and the different dilatation of the dilation of the material, okay, during the cooling phase. And this is typically, we said, about surface quenching or other type. The residual stress can be also induced by adding some material, some element in a material, and this happens in the surface thermochemical treatment, such as nitriding or carburizing, we said, or also by plastic deformation. And this is the case of deep rolling, shot pinning, laser pinning, whatever it is, or okay, everything that is able to induce also an overload, everything that is able to induce residual plastic deformation. Okay, and whatever is the nature, the origin of the residual stresses, okay, it's important to know them. Why? Because from a practical point of view, they can be used also during the design stage. If we know the residual stresses that are present in the company we are designing, okay, why? Because we have considered to apply some control surface treatment, we can get advantage by considering them during the design stage. And anyway, the knowledge of residual stresses make much deeper the knowledge than the ability, our ability to masterize and the design and the manufacture of a structural component. Okay. And indeed, why the residual stresses are not easy to measure? Well, they are self-resident in a material. Oh, thank you. Okay, they are present in the material, and so without any applied load. So how can we consider to measure them, we need or to remove material, to relax some deformation, and she should be able to relate the formed strain to the pre-existent stress state, or we should be able to measure some quantity in the material at a more microscopic scale, and then to relate this quantity that we will define to the residual stress state. Okay, this is the outline of the talk that I have already done. Also, we have already talked about this. Indeed, residual stresses are an elastic set that is present in material due to different causes we have discussed. Okay, and we can pass. Also, this has been, okay, the origin can, indeed, from a more microstructural point of view, the origin can be phase transformation, aging, precipitation of element, and multi-phase material, and then carburizing, nitrizing. From a macroscopical point of view, this can be due to thermal stresses or solidification of screen change, or autofrettage if we talk about plastic deformation. And then the original residual stress can be also combined. In welding and casting, we have some combined cause that is causing the action of the generation of residual stresses. Here we have a scheme of some of the methods that are used, the most widely used methods for residual stress measurement. I have told about hole drilling, XR diffraction. Then we have XR diffraction, anatomic strain gauge, but neutronic diffraction. And then you have ultrasonic elastic wave velocity measurement, ultrasonic method, and magnetic methods. We will focus mainly on the XRD. Why? Because it's now today widely accepted and used in the scientific and technical environment. And then we will also discuss the hole drilling method that is also widely used, with some advantages and some disadvantages with respect of XRD. And also we will introduce also the Barkhausen noise that is a magnetic method. Why I'm not considering the other one? Indeed, the other one are powerful. Neutron diffraction is powerful, is not destructive, and is able to measure residual stresses also in depth without removing any material. But we need something like a synchrotron, a very large equipment that is available just in few labs in the world, let's say. It can be done, of course, but it's not an everyday method for measuring residual stresses. Okay, and so let's start with the XRD. I will try to be as faster as possible, to shorten as much as possible the talk, so that I know that you are very tired. Okay, and then you have other phases to conclude the course. And just a few words about the nature of residual stresses of XR. Were discovered at the end of the 19th century in Germany by Mr. Röntgen. And at that time, the nature was unknown, and this is the reason why they were called X-rays, not known, unknown rays. And we know now that they are an electric magnetic radiation with a very short wavelength, that is lambda is in the order of 0.001 to 10 nanometer. And we can see here that it's out of the visible XR, is very far from the visible light frequency. Okay, it's very penetrating, we know, and we know also that it's very dangerous for human and living organics health. We know that when we are using XR also for diagnostic, for medical diagnosis, but at the same time we know we must protect, otherwise an abuse of XR should lead to serious injury, serious health problem. Okay, this is done. And this is an XR tube, an example, a schematic view of an XR tube, and two possible XR detectors. Okay, indeed, how can we form the XR? we need a very high voltage. We need an anode and a cathode, and by means of this very high voltage that is running here, some electrons are emitted by the anode, and then this by hitting a target plate, emitting XR. And this is the cathode, and the wavelength of the XR depend on the nature of the material of the cathode. Okay, and here are some traditional XR detector. Okay, this sorry for the Italian time, I didn't remember. This is, anyway, these are the XR photons. This is the cathode. This is the wire is the anode. And by means, when we are the photon and enter in the detector, there is a change of the electric signal, and finally we can relay the number of photons that are hitting the instrument, the detector, to the intensity of the XR. And this is another one, is similar, but in this case we are transforming, we are changing the frequency of the XR from the XR properly set to the visible light, and by means of a series of anode and cathode, we are able to get the wanted signal. Today there are more modern detector, that is a positive sensitivity detector, and they permit to assess, to measure the intensity on the XR not in one single point, but in a finite area. And it's quite useful also for residual stress, because in this case we don't need many to move the detector to have a special view, a 3D view or 2D view of the intensity of the XR, but just one exposition is enough, because we have a two-dimensional window that is recording the signal. Which kind of residual stress are we measuring by using the XRD? Indeed, first of all, we must distinguish the different level of scale that we can define for residual stresses. We can start from the lowest one, the so-called micro residual stress type 3. Sorry for typo, type 3. These are intergranular. The level of scale is one single grain. This means that if we are interested in type 3 residual stresses, we are interested in what's happened inside a single grain, like this black one. Here we see that we can define somehow, at least theoretically, conceptually, a variation, a trend of the residual stress inside the grain. If we enlarge the scale and we consider some grain, we have the micro residual stress type 2, intergranular. Here we are considering some grain, but still at the microscopic scale. Okay, and if we enlarge the scale, we have the macro residual stress. Now we are talking about larger areas. We are talking about a level of scale that make possible to consider the material as a solid continuum without, so defined by E and the elastic module and the new coefficient as regards the elastic properties. And in this case, we are now, this is a trend of a macro residual stress. So with the XRD, the main result is this, is the macro residual stresses. Okay, so what the number that we read when we perform an XR measurement or residual stress is the macro residual stress. Okay, a secondary result that is related to what I call FWHM, that we will define in a few minutes, is related to type 2 residual stress. That is the microplastic strain and so on. Nothing with usual equipment, nothing can be related to type 3, to the intragranular, one single grain residual stresses. Okay, which are the principles of the XR diffraction, of the diffraction of the X-rays? Indeed, the principle is the Bragg's law, the law for diffraction that was discovered by Mr. Bragg and it's written this way. We have a diffraction that if you have an incident XR beam in this direction with inclined by theta with respect of the impacted surface, we will have diffraction that is a positive reflection, let's say, okay, if this law is valid. That is lambda, that is the wavelength of the X-ray beam, is equal to what? To 2 times d, where d is the lattice spacing according to some Miller index, by HKL Miller index, that multiply sin theta, where theta is the inclination of the X-ray beam with respect of the contacted area, of the impacted area, let's say. So every time this law is verified, okay, we have positive diffraction. So if we measure what is going out of the surface, we will measure the so-called diffraction peak. If the material is a perfect crystal, we will have one single line at that angle, and the rest will be null. If the material is not a perfect crystal, such as the metal, we will have a diffraction peak. That we have not a single line, but a peak that whose geometry, let's say, whose sign is similar to a Gaussian shape, a Gaussian function. Okay? And so what this is, indeed, this is what I said, indeed. This is the Bragg law. Imagine here, this is a material we are measuring. We have no strain. Everything is, the crystal lattice is this. Okay, if the material is perfect, we will have one single line. Here is not perfect. The representation is not for perfect crystal, but almost perfect. We have a very narrow peak. Okay, if we apply a uniform strain, indeed, the lattice spacing between the crystal plane is different. And so what happens is that the diffraction, the theta, the angle for diffraction is slightly moved, is shift. And diffraction will happen for another angle. So this is also, from an intuitive point of view, if you are able to measure the shift of the diffraction due to some strain, we are able maybe to relate this to the quantitatively relate this to existing residual strain and then to the stresses. Okay, if you are applying a uniform strain like this, what's happened? It's happened that the Gauss, the diffraction peak will be wider, will enlarge. Okay, and so let's see how XR diffraction measurement for residual stress is done. Okay, we know that the material, a metal, let's say a crystalline material, is formed not by a perfect crystal, but by many crystal grains with a random orientation. The material is the same, the microstructure is the same, at least if you have one phase and everything is uniform, but we have many grains with different orientation. So here you see some grain with the crystal planes, and the orientation is randomic, let's say. Okay. So what can we do? We can apply, an X-ray beam here, and then we can measure with a collimator and then a detector, which is the diffraction that we can get by means of this. Okay, and if we want, indeed, consider this is the free surface. This is the collimator that measures the collimator measures the distance and the perpendicularity with respect of the free surface. If this is the detector, the beam ray is coming from this point, okay, and the detector, will measure diffraction when the Bragg law is satisfied, considering theta starting from the crystal planes. This is the condition for having diffraction. We are not considering theta with respect of the free surface, but we are considering the lattice spacing. And so in this position, the grains that will be inclined this way, if theta satisfies the diffraction condition, will be lighted, let's say, by the X-ray beam, and will be a signal to the detector. So not only this one, but could be one here, in a limited depth of material, because the penetration is just some micron, let's say, of XR is not very much. But anyway, we'll have that a part of this grain will be lighted by, and by the diffraction, and so we will have this, and the detector will measure that angle. Okay? Is it clear? So we start from this position. Here is the XR beam. This is reflected and is diffracted, and the diffraction will be appreciable according to the Bragg law when the beam, the inclination, let's say, of the contact with respect of some grain with this orientation is able to satisfy the Bragg's law. Okay? And then we can repeat in different positions, always in the same point. We are moving, turning the collimator this way, but finally the point where the X-ray beam hits the surface remains the same. And we can call psi the inclination of the collimator with respect of the free surface. That is not theta, it's not the diffraction angle. So theta equal to 0 means that the collimator is perpendicular to the free surface. Phi equal to 30 means that the collimator is inclined 60 degrees with respect of the horizontal line and 30 with respect of vertical line, and so on. And every time we move, we rotate, we turn the collimator, we will repeat the same operation, but the grain size, the grains that will be interested by diffraction will be different, will be the one that will be correctly oriented with respect of the new position of the collimator. So we can refer the measurement to the same point, because the beam is hitting always the same point of the surface. But the grain that will give the diffraction signal, the grain will be different. Okay? And this is a bit tricky, but anyway, they are confined in a very limited volume. Okay? So we can go back. When we have, imagine that we move and we have the desiderable, the condition for diffraction when the collimator is turned this way and eating these grains. The detector will give a diffraction peak that belongs to this grain and not to the previous one. And the same for other possible orientation, possible inclination. Okay? Any question? Okay, and we goes on. We repeat the measurement according to the impedance angle psi, and will diffract, and the signal will be a different angle theta, but the theta will be quite closer. The deformation of the single grain will be different, so theta cannot be the same, but the material is the same, the variation will be small. Okay. Okay, and this is another representation of what I said. Here we have the collimator, the detector is here. We are moving the collimator and the XR beam this way, we are turning this way, and at the same time, the detector is following the movement of the collimator. And finally, by means of the detector, we are able to see how is changing the theta angle according to different psi. And these are indeed, and now this is the way the measurement is done. Now we must, the next problem is to relate these diffraction peaks, angles, to what? To the strain and to the stresses. And so we start from the Bragg's law, lambda equal to 2 times the lattice space according to Miller index generic HKL, times sin theta. So we can define, we can write that this lattice spacing is equal to lambda over 2 sin theta, and the derivative of the lattice spacing is equal to this quantity, simply by deriving the initial function in theta. And so, if we know what is the delta D HKL, we remember the definition of strain, that is, the fact is delta D over the initial D, and we can write that the epsilon, the deformation, the strain for that lattice plane HKL is equal to minus the cotangent theta 0 in delta theta, where theta 0 is the original diffraction angle of the undeformed material. Okay? So we start from the Bragg law. We write the Bragg law in terms of lattice spacing. We derive the lattice spacing, and we found this formula. And we remember that the strain is equal to the difference between the lattice, can be defined as the difference between the lattice spacing in the condition we are measuring and the original one, not deformed, over the original one. So delta D over D0, or delta D final minus D initial DO over D initial DO. And so this is finally we find that epsilon is equal to this minus the cotangent theta 0 delta theta. And here we have a representation. Epsilon, if we are on the free surface, what can we say? That this is the vector, the deformation vector, epsilon phi psi in a generic direction, and we can distinguish the component on the 1, 2, and 3 direction, where 1, 2, and 3 are in this graph are the principal direction. Okay?
Sir, in that case, here, sir, here.
Sorry?
Here.
Yeah, for sure.
So that means the residual stress measurement using XRD is a comparative method. So we are comparing it with a component which is having...
We are comparing, indeed, we are using the measurement, and we are consider as a base condition, okay, the condition, the undeformed condition, where the diffraction peak corresponds to the peak that we have without any stress applied. Then we will see in a minute how, indeed, not all the times we know for that material, for that alloy, what's happened, which is the real delta Z, the D0, the undeformed lattice spacing. But we will see how can we solve this problem, okay, in a few minutes. Okay? Where I was? So this is, we discussed this. The other step is this. This is the relation between the strain and the stresses in principal coordinates for a plane on a free surface. That is to say, the sigma 3 is null. We are on a free surface, not loaded, and so the vertical sigma, the perpendicular sigma is equal to 0, is null. So this is what we can write. And the generic the vector strain in the generic direction, epsilon phi psi, with respect of the principal direction, can be written this way. Okay, I'm not going to develop the formula. You must trust me, this is true, it's valid, okay? Otherwise you can validate as an homework these formulas, okay? And here indeed, alpha represent this cos phi sin psi, alpha 1 and alpha 2 is sin phi sin psi, and then finally we can write this formula that relate the generic vector component, the epsilon component, the strain component vector, to the stresses, to the principal stresses, by means of the direction we have analyzing. Okay? If we consider phi psi equal 90 degrees, it means that the strain vector lies in the horizontal plane, in this direction. And so we can write, and the stress component is equal to sigma 1 cos cos 2 psi plus sigma 2 sin 2, sin psi 2. Okay? And so now we have the relation between epsilon and sigma. So we can substitute this compact formula, sigma phi, instead of this part of equation, this part of relation. And we find, okay, and we find that a much more compact version. So epsilon phi psi is equal to 1 point plus the corresponding coefficient over E elastic model that multiply the second power of sin quadro psi, sin 2 psi, minus the sum of the principal stresses that multiply the Poisson ratio and divide the elastic modulus. Okay, and this is the way the formula is written by considering that compacted way. Okay, so this is a formula that we take in mind, that we note, and we now remind the definition of epsilon with respect of the lattice spacing that we have already defined a few minutes ago. Okay? And so what can we say? We can, instead of epsilon, we can put here the definition of epsilon, delta D over D. And this is equal to this quantity. And finally, if the variable is considered sin 2 psi, this is a line, a straight line. And so we can, by deriving this straight line with reset of psi, we can obtain the final equation that gives us sigma phi, the stress that lies in this direction. That is equal to what? To E over 1 point nu, Poisson coefficient, that multiplies 1 over D0, the initial lattice spacing, the undeformed space, that multiplies the derivative of the lattice spacing with respect of sin quadro psi. So delta D over on sin quadro psi, okay? On delta sin quadro psi. Okay, and and so, what can we see here? The angle that appears here is psi. And psi, we define psi also as the angle we are turning the collimator. It's the same angle. So if we change psi by turning the collimator, we are obtaining every time, we should obtain sigma phi. And what can we obtain by using different XR measurement? We are obtaining something like this. If we have a linear relation between sin quadro psi and delta D. And this is the linear that comes from this equation. And then, by considering the derivative, we can calculate, according to the elastic model and the Poisson coefficient, we can consider to calculate also the residual stress. So we can consider the different diffraction point. We know the angle. By means of the angle, we can calculate delta D. By means of delta D, we calculate sigma phi. That is related to the slope, of the straight line that relates delta D and sin quadro psi. So the angle of diffraction with sin quadro psi. The problem, what could be a problem? As Basil said, we have delta D over an initial D, D0. That is the theoretical one. What's happening if we do not know delta 0? Indeed, generally we can do this way. We use the first diffraction angle, psi equal to 0, perpendicular, okay, as instead of D0. Why? Why we can do that? Because in the end we are using the ratio between delta D, that is a very small quantity, with respect of D. Indeed, the ratio will be quite small. Nothing changes if we are using D0 or something that is not D0 but is quite similar to D0. Okay, one measure point, one measure value. In the end, nothing is changing. The error is negligible. Okay, what happens if we divide 1 over 100,000 or 1 over 100,010. The ratio remains the same, and the same happens here. Okay, so it's a law to consider the first delta D that we obtain, as D0, and then use the other one to calculate delta D0. Okay? So, by means of the law, we are calculating delta D0 according to different psi, and by deriving the straight line, we know that the slope, okay, is related to sigma phi. So the sigma, the stress that is acting in the direction, in the plane, so is included in the plane, in the free surface, in direction psi with respect of the principal coordinate. Okay, this is basically what we are doing within XRD. There indeed, we do not to do this operation by hand. There is a software that gives out the result, and here is this is just for showing you the different. You see here the slope m is equal to 1 over from mu over e that multiplies sigma. So once we know the slope of this straight line, we know sigma, and we know that if the slope is positive, okay, we will have a positive residual stress. If it's negative, we will have a negative residual stress. Okay, the sign is also already defining the sign of the residual stress. Is it clear, the concept? So we use different angle of attack, let's say psi angle. Okay, for each angle we are measuring a diffraction peak, theta, and we can read by means of the Bragg law, we can relate this to the lattice spacing. And it will be a bit different with respect of the angle we are using, because the grain we are considering are different, let's say. Okay. Then what can we do? We use the theory of elasticity and the formula that relates stress and strain. We remember the definition of strain, and at this point we are able to define delta D. That is the difference between the D that we have measured and an initial one. Delta D over D is epsilon, and by means of the formula that I have shown, that is shown here, we can relate the result of the XR diffraction measurement with epsilon. And each angle phi that we are using will give this epsilon vector, where epsilon phi psi, where phi remains the same, this one, psi is varying with the collimator. And then, when we derive the expression, we find sigma phi that is with psi this way, that is in plane. Okay, of course, cannot have a component out of the plane because the surface is unloaded and is free. Okay. Okay, so and then by deriving, by the slope of this straight line is proportional to the residual stress by means of the elastic constant of the material. Okay, any question? Let's see and discuss some practical problem related to the application of XRD. Indeed, the first is the choice of the right radiation. Indeed, not all the material react the same way with respect of the XR that we are using. If we are using for generating XR a chromium anode, okay, a chromium radiation, this will be good for some material because we'll be able to cause diffraction for aluminum alloys, for instance, for many steels. Okay, but will be not good for inconel forces. Why? Because in this case we did a copper radiation. So the nature, the material of the XR tube is important and should be varied, and we should be checked with respect of the material we need to measure. Indeed, from a practical point of view, if we have a chromium tube and also a copper tube, we are able to cover almost all the material that are commonly of interest for us. Not all, but most of the material. Okay? Copper and chromium, yes, copper and chromium. And this is the first practical point. And in this table, you can see some information also. The lattice plane that is interested by the chromium radiation, for instance, or from other radiation, the diffraction angle to theta that we should expect to investigate for each material, the elastic constant of the material that are referred to that lattice plane and not to the bulk, and so on. Okay. The second problem can be the in-depth measurement. Indeed, we have already discussed about this. The penetration of XR in material is quite low. So if we want to measure not only the stress on the surface, but the profile, the in-depth profile of the residual stress, we need to remove material. And we need to do that by means of not a mechanical tool, because otherwise we are changing the residual stress state and we are generating new residual stresses, but we need to use an electrochemical method, the electropolishing or chemical polishing, in such a way that the material is removed without a mechanical action. This is the final result of a localized removal of material. This is the probe that is used for removing material. This is connected to an electrochemical circuit, of course. And then here there is the dial that make possible, similar to the Holman gauge dial, let's say, that is able to measure how much we have removed, the depth we have removed. Okay. This is a local tool. There are other tools where if you have a cylindrical part, we can immerse the cylinder and we have a uniform removal material along the external circumference. The peak determination. How can we measure the peak? How can we consider the peak? Which is the real peak? Indeed, we have a series of points and we have a peak. How can we determine the right position? We can approximate the series of points we have with some mathematical formula, with function. Or the parabola, we can fit the point in such a way that they are a parabola, or a Gaussian fitting, or we can also consider the area described by the point and consider the angle where there is the centroid of this figure. Okay, or also the cross-correlation method that here is described that is also used for this kind of thing. Indeed, let me say that if the measurement is reliable and well done, okay, each of these methods gives the same result with a variation that can be 2, 3, 4%. Otherwise, it could be necessary to make some preliminary study and then to see which is the best fitting method that is able to give you to reduce the scatter and so to give you the best result. Okay. Which is indeed, I have commented and I said that the relation between del D and sin quad of psi is a perfect line. This is the ideal condition. Many times we are close to this condition. Other times this is not true. And we have something like this or like this. If we have something like this, it means that the residual stress state is not uniaxial and there is a shear stress just under the surface that is changing the final line. So in this case, there are other formulas generally given by the software that enable to anyway to calculate which is the residual stress. But the formula, not the previous one, are a bit more complicated. If there's something like this, the causes of this problem could be different, and they could be associated to some preferential orientation of the grain on the surface. that make this problem. In this case, in some time, or big range data, something like this. In this case, what can we do? In general, we introduce a small rotation of the angle C during the measurement, some decimal of degrees, okay? In such a way that this effect is sometimes reduced. Sometimes it's good, sometimes nothing is changing. Another possible cause of inaccuracy is if we have to measure strongly curved samples. In this case, the collimator must be very, very fine. Otherwise, will be the focus of the X-ray beam cannot be the same along the curved surface. And so we have to consider this, and finally the counting of the photon will be small. The incorrectly determined elastic constant, indeed, from this point of view, most of the time we rely on the constant from reference data, from the software. If the material is new, since we do not need the bulk elastic constant, but we need the elastic constant according to that Miller plane we are measuring, HKL we are measuring. If you don't have any data, we should perform some preliminary measurement to determine, with a known case, to determine this constant. What does it mean? We could use a thin strip, completely stress-free. We apply the known bending moment. We know which is the final stress we should expect, and then we calibrate the elastic constant in such a way that we find the stress value we know. Okay. And also if you have a very composition gradient, if you have a very steep gradient, some inaccuracy could be usual, let's say. Okay, this is for the XRD. Any question? Yeah.
Sir, slide 20, I guess.
20? 20?
The previous one, the previous 19. Yes.
Okay.
Sir, in this, sir, as we can see, the 2 theta angle, we have gone up to 140, 150. The diffraction angle, we have gone up to the values of 140, 120, 130. Likewise, we have gone.
Yeah.
But in general, mostly when we do the experimental studies, for obtaining the XRD peaks, we limit our study up to from 10 degree to maximum like 80 or 90 degree. So is it like for the residual stress measurement, is it the reason why we are going for diffraction angle till 140 or 180? Because say for example, the last one, TI6AL4V at the bottom, if we actually try to figure out the XRD pattern of TI6AL4V, we could actually get it in between 10 to 90 degree diffraction angle. But here, I think they have gone up to 140 something. So what might be the reason we are going for a diffraction angle? Why we are actually making the XRD to go in?
Why we use this angle, you mean?
Yes,
and
sir.
not other one?
Because normally we would get the, if you are trying to get the peaks of titanium or vanadium or the other alloys, we would get in between 10 and 90 degree. But
okay, no, I understand. You say we have also other angle where we have diffraction for titanium or other material. Why we are using this one that are a bit far from the usual range?
Yes,
okay,
yes.
Indeed, because it's believed that this angle can give a good response in terms of peak that we can analyze. But another reason is this: we are measuring residual stresses on many times, not on small sample, but on large components. And we cannot put the large component in a lab diffractometer. That is to say, we cannot move the small sample with respect of the XR beam because they are too large. The component is on the ground, on a table, let's say on a desk, and we move the XR system according to this, with respect of the sample. And these angles are the ones that make possible a convenient design of the instrument, of the collimator and the rest of the, make it portable and suitable.
So
It's a practical reason,
it
but
cannot be performed on the normal Bruker XRD or something like that if the XRD manufactured by Bruker company, I mean, which can actually accommodate only very small sample. This is one another setup which can actually find out the residual stress for a larger workpiece. Is that what you want to convey, sir?
But you mean if what's happening if you're measuring different angles?
No, sir. What I'm asking is, in the labs that we have got a Bruker-made XRD.
Okay,
The sample is very small.
And you move the sample.
Yes,
Okay.
and
you are able to scan 360 degree in the end, more or less, but a very wide angle arc.
No, it is capable of moving. I think 180 degree it is capable. But then, since it is small, within a range of 10 to 90 degree, we would get that particular peaks what we require generally. But the setup that you are suggesting, is it like a portable?
It's a port, and the angle we can use is limited. Okay, it's in terms of C, and this corresponds to this angle are the most convenient one. Okay, also for steel, there is not only 156, but the response is good, and it's also good for the portable equipment, because we already know the angle we put, and we can scan a limited range that is compatible with the instrument, and finally find the residual stresses. But it's also true that if we are measuring the residual stresses according to different HKL planes, the result will be a bit different. This is for sure. Do not expect it. And also, if you have a two-phase material, and we measure in a different moment one phase and the other one, in the same point, the result can be different. It will not be the same. For the reason the measurement is done.
Okay, sir. Thank you.
Okay, and if you ask me about the accuracies of this portable equipment with respect of what you have in the lab, indeed, the accuracy of these portable units is a bit less than the lab one. But the advantage is when we can measure not small sample, but even very large part. We can also put these devices in the back of a car and go in field and measure pipelines or something, or bridges, steel bridges, this kind of things. Okay. Indeed, the time is short, but anyway, let me introduce the old drilling method. Here, the theory is quite different. Here we are not measuring the residual stresses in the point, okay, that we are analyzing. Here we are considering a strain gauge rosetta with 3 strain gauges with a known relative direction, and we consider the center of the circle that is of the rosetta, and then we consider to drill a small hole at the center of this circle. And these are the common rosetta that I use for this kind of measurement. This is the blind hole that is drilled. And then by measuring the deformation that are relaxed during the drilling, measuring the deformation at the point of the rosetta, so not the same point, of course, we are able, by means of theory elasticity, to relate the relaxed deformation to the pre-existing stresses in the point where we have cut the drill, where we drilled the hole. Okay? And indeed, these are the formula that I don't want to go in detail into the core formula. Indeed, the method was defined initially for uniform stresses, and then was also improved by means of defining proper coefficients that were obtained by means of finite element. In the end, was Mr. Shire that was the father of this of this technique, in the end, we were able to use this method also for not uniform residual stress measurement. Okay, but even if we are interested just to the surface state of residual stress state, we need to drill a hole. The method is destructive. And this is what the way it works. So these are the coefficients that are used, that are obtained by means of finite element, that are used to relate the pre-existing state at a point with the relaxed deformation according to some depth of the hole itself. These are some of the characteristics of these three types of Rosetta, A, B, and C. And the method can be also adjusted, let's say, if you are considering not only elastic relaxation, but also elastic. The stresses are in the elastoplastic field, let's say, have a plastic component. But in this case, it is recommended to use 4 strain gauges Rosetta, not 3 but 4, for improving the accuracy. And now the third method, the magnetic method, okay? Indeed, this is the less theoretical one. That is to say that we are talking about magnetic method. Indeed, we are exploiting what? The bond between magnetization and elastic deformation. What does it mean? That the magnetic behavior of a material can change according to some elastic deformation. Okay, so from a microscopical point of view, the material can be considered as formed by magnetic uniform zones that are called the magnetic domains, we know. The domains orient themselves in relation to the direction of the applied load. So if you apply the load, the domain magnetic will be oriented according to the applied load, especially if we apply a tension or a compression, we will have an orientation of the magnetic domain that will be opposite. And this is what we are exploiting by considering the Barkhausen noise. The Barkhausen noise is a magnetic noise. Okay. What's happened? Imagine you have a coil of a conductive material that is placed near the surface of the sample, okay, here, and the change of magnetification induces an electric sigma that is in relation with the stress state of the material. This is the base of the magnetic noise. So we have we apply unit, magnetize, we apply the magnetic field. Here is the sample. It changes, the signal is detected, is amplified, and then is displayed. Since the orientation and so the signal is related to the sign of the residual stresses, by means of the analysis of the signal, we will be able to say if the stress is compressive of the side. If furthermore, we have available some calibration that relates to the same material with the same microstructure, we can also try a quantitative estimation. We can try to say that it's not compressive or tensile, but is minus 400, minus 300, but it's quite difficult, let's say. Okay. Okay, so by summarizing, the measurement is conducted by exploiting the fact that the presence of residual stresses affect the orientation of domain. If you have compression, something like this. If you have tension, the signal will be higher. Okay, this is with magnetic with positive magnetostriction. So steel and iron give this signal. If you have compression, the result that the amplitude of signal is reduced, the hysteresis is enlarged. Otherwise, if you are in tension, the hysteresis, the magnetic hysteresis is reduced and the signal is higher, the amplitude is higher. If we have material with an opposite behavior, negative magnetostriction, such as the nickel alloys, we have the opposite. The tensile stresses reduce the Barkhausen noise. Okay. Is good, is bad. Barkhausen noise is very good for for application in product line. Okay, if we have to check the quality of some machining and we need something fast, not destructive, the Barkhausen noise is the best. You can put in between two stations, the measurement is quite easy and fast, and you have an idea of plus and minus. And many times this is enough. It's enough to know that in one part, grinding is not considered, is not causing tensile stresses, because this makes the part to be discharged. Okay? But if we are thinking to quantitative evaluation, quantitative measurement, this is not a bad way to proceed. Why? Because the Barkhausen noise depends not only on the residual stress, but many other factors, microstructural and so on. So if we don't have a very, very fine calibration on a part that is stress-free with the same microstructure, the same grain size, and the same everything of our part, the quantitative relation is not accurate. Okay, so some comment. The affected depth is around 1.5 millimeter. We need calibration test. It's good if knowing the sign of the residual stress is enough. Okay. For high level of stress, the signal could be saturated, so we do not appreciate any variation anymore because we have saturated the signal. I said that Barkhausen depends on other factors, and this is a problem. And indeed, let me add that we need customized probe like this. This is for gears, and if you have another geometry of another kind of gear with a different pitch, you need another probe like this. Anyway, indeed, the validity for a possible tool for inline in a production line, this other application are good. Many times I said, a typical application is to check if grinding is abusive grinding or not. Abusive grinding that the parameter for grinding, are too severe, and we are burning the surface. We are inducing tensile residual stresses. And if this is the problem, and in aeronautics is an urgent problem, Barkhausen noise is the best option. Okay, for abusive grinding and so on. And then we are at the end. In this table, we have some comment about the different techniques that with practical issues, and then to be considered if you are going to consider to buy one of these equipment. Okay, and here we have a series of tables. Here you have the size of component is a diffraction, all drilling diffraction. It's not in the old drilling. A problem could be due to the curved geometry, because the coefficient we have available by the ISTM code are determined on flat surfaces. If we have a very curved surface, some deviation could happen. Okay, and then you can see here that if the method is destructive or not, if lay-based or portable, and we see the old drilling, the XR diffraction are good. The cost of measurement, indeed. Let me say that in this table, the cost of a measurement it's not well clear, because if we refer to XR, this could be fine. Around today's could be in euro, could be around 200 euros or pounds. But if we talk about oil drilling, it should be a bit less. Also because the equipment is less expensive than XR diffractometer. Okay, for sure the synchrotron, the neutral diffraction is much more expensive, but with other limitations. It is limited to laboratory and not portable. And we did not talk about the ultrasonic, but this is an object of the researchers are changing the propagation speed of ultrasound in metals. And also in this case, we need a fine calibration because this quantity is also a function of other variables. These are possible material issues to consider with the surface condition that we need, okay, and then the surface preparation, if it's coated or not, and this kind of thing. And indeed, for the XR diffraction, the limit is that we need, if we want to have a diffraction, we need a crystalline structure. Otherwise, diffraction is not possible. Okay, and so metal and ceramics. Magnetic, Barkhausen is even more strict because we need ferromagnetic materials. Okay, and in terms of preparation of surface, indeed, since the hole drilling is considering to drill a hole, the preparation is less important than other part. Then physical characteristics. Okay. And here you see some remarks, the resolution, the stress type that we can measure. And this is important, this is interesting. The stress type, by means of the hole drilling, we are measuring macro residual stress. The XR, we can measure the macro and micro residual stress. Oh, I forget to tell you about the FWH, okay, the full width at F maximum. What is, if we have the diffraction peak, this full width at F maximum is the width, the angular width of the peak at half the maximum. And this quantity is related to micro residual stresses type 2. So it is related to micro plastic strain. And this is the reason why I said yesterday that this kind of signal is related to hardness, is related to the way shot peening is able to induce surface work hardening. So when we have in a shot peened material, most of the time when we have full width FWHM is increasing, it means that we are inducing more plastic deformation, more surface work hardening. Okay? And this is the final one, this slide, where we have advantage, disadvantage. We have already discussed about the pros and the cons of each of these techniques, at least the one that we have considered, the hole drilling and XR diffraction. The hole drilling is quick, simple, is portable, widely available, and deep hole drilling for thick section component. On the other side, the interpretation of data could not be clear, is destructive, and limited strain sensitivity and resolution. The XR diffraction is versatile, is available widely, is also portable, and also micro residual stresses can be measured, as we said. The cons are indeed, indeed, if we consider for lab-based systems, just small component, but this is not a limitation for portable ones. And the magnetic, indeed, let's go to the magnetic method. It's very fast, is portable, but they need to separate the microstructure signal from due to the stress. This is the problem. If you have not an accurate calibration with some accurate reference sample, the quantitative evaluation, quantitative determination of the residual stress are not possible. And I think that this is the last one. This is now I have really concluded my talk, and I thank you, and I'm here for questions. Thank you again for staying here.